Hello everybody, and welcome to an extra lecture segment for 6838. Now, in this segment, I thought I would essentially patch up one missing piece that I kind of zipped through toward the end of our previous lecture because we ran out of time, and that was an example of optimization on the Stiefel manifold. And in particular, we can derive algorithms for principal component analysis, or PCA, and many variations of PCA using the machinery that we developed in lecture. Now, I suppose I should be a little bit careful here. When I say manifold methods, I don't mean manifold PCA. I really mean manifold optimization methods for PCA. So, for example, there are algorithms that try to do principal component analysis on curved spaces. That's not what I mean here. What I mean is just using manifold optimization to solve PCA type problems. And the problem that we briefly stated in class and then I punted on is the following. Essentially, it's a max over a set of matrices X, which are in Vk of Rn of the Frobenius norm of X transpose A. So X transpose A, you can square it just for convenience and take the Frobenius norm. Now, if you'll recall, the set Vk is the set of matrices that have k orthonormal columns that are all in Rn, right? This is the Stiefel manifold. So if k equals n, this is a set of orthogonal matrices. When k is equal to 1, this is the basically set of unit vectors. And in between, it's something else. So here, essentially what we're going to show is that this problem encapsulates principal component analysis if we think of the columns of our matrix A as data points. And we'll see how that enables us to basically come up with other variations of principal component analysis quite quickly, and then to optimize them efficiently using just generic first-order manifold optimization methods like what we derived in class. So to start, let's actually derive the relationship of this formulation to principal component analysis, or PCA. So in order to do that, we can compute the singular value decomposition of our matrix A. So in particular, we will factor A equals U sigma V transpose. Remember how SVD works here. So U and V are orthogonal, and sigma is a diagonal matrix of singular values. And now we can take our objective function and write it differently. Now, this isn't to say that in manifold optimization we actually have to compute the SVD. This is just an argument to tell us a bit more about this optimization problem. Okay, so in particular, we have X transpose A. We take the Frobenius norm squared. And now we can plug in our form for A. And what do we get? We get X transpose U sigma V transpose. Frobenius norm squared. Okay, so one useful property of the Frobenius norm is, by the way, in our particular SVD, let's assume that V is square. We can always do that. And in particular, if you multiply a matrix by an orthogonal matrix, or a matrix with orthonormal columns, then we can see that that actually doesn't affect the Frobenius norm. That's just a linear algebra exercise. So this is, in fact, equal to the norm X transpose U sigma, assuming that V is squared. Okay? And, well, we can just give this matrix here a name. Let's call this X bar. And one thing that we can do is use the compact SVD. So U and V are both square, and then sigma is the non-square one. The details here don't matter a whole lot. You can kind of Google this at home. But the basic point here is that I'm going to make a new matrix X bar, which is equal to X transpose U. Or actually, maybe just for consistency, I'm going to go against my notes a little bit. Yeah, I'm going to say that this is X bar transpose is equal to X transpose U. And if I do that, well, what is U? I mean, it's just like a rotation or orthogonal matrix. So it doesn't actually affect the property of being in Vk. So in particular, X bar is also in the same Stiefel manifold, just kind of rotated from X. Okay? So in other words, I can write a new optimization problem, which is equivalent to our original one, and looks like max over X bar in our manifold, like that, of x bar transpose times sigma. And here, remember that sigma is diagonal. It looks like sigma 1, sigma 2, dot, 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 like that. Frobenius norm squared. And without loss of generality, we can assume that our singular values are sorted from biggest to smallest. Okay, so again, what did we just do? Well, we started with our original manifold optimization problem. I introduced the SVD of our input matrix A. Remember that our variable here is x, it's not A. And just by doing a little bit of algebra and a change of variables from x to x bar, we can see that this is sort of equivalent to this maximization problem over x bar in the same manifold, but now multiplied by a diagonal matrix of sigmas. Now, if the sigmas are sorted, then a very easy thing that you can convince yourself at home is that the best way to make this norm as large as possible is to just select out the k largest singular values. This is basically a corollary of the fact that if a bunch of vectors are orthonormal, then they at most have value 1 in any slot. So in particular, you can convince yourself that the optimum of this problem is pretty easily equal to the matrix whose first column is the first standard basis vector, the second column is the second standard basis vector, and so on to ek. And okay, well, if we unroll, remember that x transpose is x bar transpose equal to x transpose u, or equivalently, I guess, x bar is equal to u transpose x, right, just by transposing this expression here. Well, okay, so in that case, essentially what are we doing? Well, here, okay, so in other words, x is equal to u x bar. Well, what does that mean? Essentially, we're taking u and multiplying that at a matrix that is just picking out the first k columns. So essentially, what that means is that we can think of x as, without the bar now, as just, the principal component directions, u1, u2, uk, which are just the columns of u that correspond to the top k singular values of our matrix. Okay, so essentially, this argument, which I admittedly zipped through a little bit, is intended to show you guys that if you start with this optimization problem here, where you're maximizing x in our manifold vk of this x transpose A quantity, then just by plugging in the PCA, or rather the SVD of A here, you can convince yourself that x is just comprised of the top k singular vectors of A, which is exactly the PCA directions that you know and love from statistics or linear algebra. Okay, so the basic point here is that this optimization problem is equivalent to principal component analysis. Now, why is that useful? Well, essentially, what it allows us to do is to modify the principal component analysis problem in different ways by essentially introducing some regularizer to our problem that can promote different properties for our principal component directions in x, right? So I could introduce some function of x that makes x have a particular form. And now if I just use manifold optimization for solving this kind of a problem, it's really no harder than solving the original problem, right? They all just involve computing an intrinsic gradient and then doing, first order steps in that manifold. So next, let's talk about two different variations of this basic model, right? This is the PCA model. Hopefully I've convinced you of that. Now let's talk about two different, more modern takes on principal component analysis that try to promote slightly different matrices X than what you would get out of the classical case. Okay, so let's think about some variations of the PCA problem that we can get by just basically messing with the objective function here, and then our manifold optimization algorithm can just as equally work with these variations as it can the original problem. So one example here is what you might call robust PCA, or sparse PCA. actually, I don't like the term robust. Let's talk about just sparse PCA first. We're actually going to return to a different model of PCA that I think of as robust PCA. In any event, in sparse principal component analysis, what we want is that we'd like to promote 0 elements in our matrix X here. Remember that X, like if I have a bunch of data points in A, then essentially I can think of X as sort of the axes along which A is varying, right? That's what principal component analysis is doing. So one thing that you might want in sparse principal component analysis is that you sort of have this additional assumption that there's some dimensions in A that are irrelevant. Like maybe I'm, measuring the, correlation between the height of a plant, the amount that I water it, the amount of sunlight that it gets, the amount of fertilizer, and also, the height of the person that's watering the plant. So I expect there to be 0 correlation to that last thing, but maybe just due to numerical or statistical coincidences, there's some tiny correlation that gets captured in PCA. So in sparse PCA, I want to promote zeros in my matrix of PCA directions, which is essentially saying that there's some statistics in A that are irrelevant. Well, one way to make vectors sparse in general is to use L1 regularization. This is, I think, sort of a common technique where essentially what we do is we add the L1 norm of an unknown in an optimization problem. And essentially when we do that, this sort of tries to make our unknown variable have as many zeros in it as possible. This is a relaxation of the L0 norm. Well, it's very easy to introduce L1 regularization and do some kind of sparse PCA into this formulation here by just adding a second term. So here, again, we have X. We still want it to be orthogonal because it's still a set of PCA directions. And now, if I want to publish a new machine learning paper by proposing a variant of PCA, in fact, I'm sure that this exists and was proposed in some famous paper or another. Here's one way that I could do it. Well, here's my original term. And now I'm going to regularize it by adding, this is a minus because I've written it as a maximum problem here, but the sum over ij of the absolute value of the element ij of my matrix X. Right, so this problem is saying what? It's saying essentially, find me a set of directions that looks like a set of PCA directions, but also prefer my matrix to be sparse, meaning that some axes are just zeroed out. Okay, so in contrast, now let's actually derive what I would call robust PCA, which is like yet another optimization formulation here. I guess I should write it out. So in robust PCA, maybe my data has some pretty clear trends, but every once in a while I have an outlier. So like maybe, my data really clearly sits on a nice line like that. And then unfortunately, there's just some point sitting out there that's garbage. So in robust PCA, what I would prefer is that all of the big objective value kind of is used to find this one bad point rather than trying to spread the error out over our whole data set. Because otherwise, one thing that often can happen in principal component analysis is the one bad data point will rotate all of the axes out of the way a little bit. Well, now I want L1 norm, but I want it on something a little bit different. Like the set of things that I want to be sparse in this case is the set of points that are not explained well by my PCA model. So here's one clever way to do that. This is proposed in yet another research paper. All of them are listed in that giant table that I mentioned at the end of lecture. So let's think of our matrix A as a bunch of data points. Like here's A1, A2, A3, and so on. Well, then I can think of cooking up a mixed norm problem as follows, where this is mixed norm in the matrix sense. I can sum over all columns, like over all i's here, look at x transpose ai, which are like the coefficients of ai in the x basis. Now, if I take the norm of this, now it's just the 2 norm, because we're doing one vector at a time. If I were to square this norm, then that's actually identical to the original problem, right? The Frobenius norm is just the sum of the squared norms of all the columns. But one thing that I can do, which corresponds, I always get it confused if it's the L12 or the L21 mixed norm. But in any event, one thing that I can do is instead optimize the sum of everything not squared. And then what we're doing essentially is we're looking for some kind of L1 regularized set of things that, where the set of objects with non-zero error is as sparse as possible, right? It's like the L1 norm of the set of error vectors. Now, one thing that I'm getting myself confused about at the moment is that we've written it as a max problem. I'm used to thinking of L1 regularization problems as min, but I'm going to omit that in the front. But essentially, if we think of this formulation here, it's essentially summing over all the columns, but just not squaring the norm of each inner product. And the end effect is going to be that essentially it's sort of detecting outliers and putting all of the error on those, rather than putting it in just a few. Now, actually, the reason that I don't totally like this formulation here is that there's a max issue. So instead, just to be totally clear, here's a way to write it as a minimization problem. This one should be fine, which would be to take x in our same manifold again. And now we're going to sum over all the columns I and look at the residual ai minus x transpose ai and take the norm of that and not square it. This optimization problem certainly makes sense and is looking for a sparse set of columns whose residual is non-zero. Okay, so sorry I talked in circles a little bit here, but let's see if we can compare our two formulations. So over here we have sparse PCA, which is saying that I want my PCA directions to have a lot of zeros in them. So one way that I can do that is to just add an L1 regularizer to my original PCA problem. Right, so I took what I already convinced myself was PCA and just added an L1 term. A different thing that I could do is derive robust PCA, which says that most of my data is really reliable and lives on this low-dimensional subset, but there's like a few data points that I don't like. So what did I do? Well, as I was talking and thinking about it, I got myself a tiny bit confused, but this formulation makes a lot of sense, which is to say that I'm going to take each data point and subtract off its projection onto our PCA axes. Notice that I just snuck in an extra x here to write it back in the proper basis. And now I'm going to ask that the set of columns whose L2 norm is non-zero is sparse, which I can do by taking an L1 norm on this sort of set of norms here. Okay, so I'm not confident that this is the formulation that actually exists in a research paper on robust PCA, but I think the reasoning is roughly correct. The high-level point here, unfortunately I don't have enough time to re-record this, is that there are many variations of PCA that you can cook up by like adding additional objective terms or maybe changing the norm in your optimization objective from Frobenius to like L1 or something else. There are many different ways to write down the principal component analysis problem that promote different structure in your X than the sort of classical choice. And typically, this is a bit of a headache because, well, we know how to solve PCA just using singular value decomposition of a matrix. But if I add any of these additional terms, well, now that no longer works, right? The PCA argument falls apart that connects it to basic linear algebra. So we need another optimization algorithm. And one very simple one is to do manifold optimization on this Stiefel manifold. So in order to do that, all we have to do is compute the intrinsic gradient of whatever our new objective function is and plug it into our manifold optimization algorithm. So just for fun, we'll conclude with one little bit, which is to compute the intrinsic gradient of this term here. Okay, so in order to apply manifold optimization to these kinds of problems, essentially all we need to do is compute the intrinsic gradient of our objective function with respect to our unknown matrix X, and then we can use the first order gradient descent-like algorithm that we mentioned in class, just using that retraction that we derived in lecture. So for example, let's say that I just want to solve the classical principal component analysis problem given here. Right, so then our task is still the same, which is to say we need the intrinsic gradient, which remember is like the gradient of our objective function restricted to move only along the manifold, in this case of matrices with k orthonormal columns. Now, to see this in detail, I encourage you to take a look at Abziel's textbook. I think it's on page 81, which is linked in the course materials here. So if you recall, in lecture, we derived the tangent space, right? We said that the tangent space at a matrix X of our Stiefel manifold, Vk of Rn, can be written as follows, right? It's the set of matrices xi. I should have chosen a Greek letter that I can actually write. Oops. That satisfy the condition X transpose xi plus xi transpose x equals 0. Got that by just differentiating the orthonormal condition. So one thing that you can check is you can compute the orthogonal complement of this space pretty easily. In particular, you can check that if we look at the complement, so Txvk of Rn, well, somehow this kind of looks like an anti-symmetry condition. And so when we compute the orthogonal complement, that's exactly what ends up happening is you get sort of a symmetry condition that's rotated by x. So you get x times s, where s is a symmetric matrix. This is a pretty easy condition to check. Okay. So in this case, it turns out that essentially, if I want to project onto the tangent space, like Tx vk of Rn of z, right? So z is a matrix, which is like a vector on our manifold, and we want to project that onto the tangent space. Well, you know, it essentially takes z to the following, which is z minus x times the symmetric part of x transpose z, where in general the symmetric part of a matrix is just equal to the average of the matrix and its transpose. And this thing happens to be equal to, well, you can write it as I minus x transpose z, right? This already kind of looks like a projection, plus x times the skew part of x transpose z. Now, all these formulas are actually not so hard to derive. I think the easiest way to do it is kind of rotate into a space where the x's are just the principal, or what do you call it, the standard basis, and then rotate back out. But in any event here, the skew part of a matrix M is equal to 1/2 M minus the transpose of M. Okay, so we can compute the gradient of our objective quite easily, right? So we have that the gradient in the extrinsic space of, I guess, n by k matrices of x transpose A Frobenius norm squared, well, remember that this is the same as the trace of what, I guess, A transpose X, X transpose A. So when you go to matrixcalculus.org, you'll find that that is equal to 2AA transpose X. But remember the basic issue here. We have this manifold of matrices whose columns are orthonormal. But now, when we compute the gradient, it's in like the extrinsic space of all possible matrices, and it may like point some skew direction off of the manifold. So we have to project it back down onto our space in order to get the intrinsic gradient, right? That's essentially what this calculation is doing. It's taking the gradient in the outer space and just putting it back into the tangent where we can actually move around on our manifold. Okay, so in particular, all you have to do is that, assuming that we're just going to inherit the metric of the outer space restricted to the tangent plane, I just need to take this vector and project it onto Tx of Vk. Okay, so how do I do that? Well, I can just plug into this formula on the left-hand side, and I get that the gradient intrinsic to Vk of Rn of our objective function for PCA, x transpose A Frobenius norm squared, is equal to 2A transpose x minus 2x times the symmetric part, x transpose A transpose x. Okay, and that's just obtained by plugging in for z this particular gradient here. This is z. Whew. Okay, so how do we do principal component analysis using manifold optimization? Well, we already have a retraction that works on Vk. We derived that in lecture. So essentially, in order to run this gradient descent-like algorithm, all we have to do in every iteration is compute this quantity and just put it into the retraction using the formulas that we gave in class, right? So in particular, I guess, in each iteration, what do? We have like, you know, the retraction of centered at x of minus the step size times the intrinsic gradient of our objective function of this thing, x transpose A. And we derived the retraction formula in class, so we actually have everything we need to do manifold optimization to implement principal component analysis, which is pretty cool. Incidentally, this also gives you an alternative way to compute the SVD of a matrix, I guess, now that I think about it. I'd be curious if it's an effective algorithm or not. So if somebody wants to try it and send me some MATLAB code, I'd be really curious to see. Okay, so what is the high-level story of our little discussion here that I've managed to fumble a bit? Well, essentially, it happens in 4 parts. I even numbered them off. So first, I showed that this optimization problem is equivalent to principal component analysis on the columns of A. And that's a simple argument. It just involves plugging in the SVD of A, which is what defines principal component directions. Then parts 2 and 3 are just 2 different variations of PCA that I can get by just messing with this objective function, like adding a regularizer that wants x to be sparse, or changing the norm here so that it promotes robustness. And the basic point of those 2 things is just to say that this basic model can be, once you view it as an optimization problem, it can be modified in different ways that are quite useful in practice and can take care of some of the downsides of principal component analysis. But if we're going to use those models, we no longer can use the SVD of A because we've changed our optimization problem. But thankfully, these manifold optimization algorithms still work. All you need is a gradient. And so just as an example of how to compute an intrinsic gradient on this particular space, we did it for the basic case of PCA without a regularizer. And this is just an extension of the computation we did in class. So here's our tangent space, its orthogonal complement. And putting these 2 things together leads us to a projection operator. So essentially all we have to do is take our PCA objective, differentiate it in the extrinsic space of all n by k matrices, and just project it down into the tangent plane. That's what we did here. And once we have the gradient of our objective function on our manifold, then our algorithm, you just turn the crank. You just follow that retraction formula we had in class. So anyway, I'm not sure if this extra segment is going to help or hurt. I could have done it better. But the high-level point is that one of many things that are enabled by this manifold optimization perspective is a way to implement a whole class of different principal component analysis models just by modifying the objective in simple ways and computing gradients. Neither one of those is particularly complicated. So with that, I'll see you next time.